Hello everyone, my name is Bramastya Giri and my study number is 24055311075. I want to explain Manufacturing, Engineer and Technology book, Chapter 2, and the title is Mechanical Behavior, Testing and Manufacturing Properties of Material. First slide is Introduction. Mechanical behavior of material. Mechanical behavior refers to the way a material responds when subject to force, stress, or environmental influences. Understanding these mechanical properties is essential for predicting how a material will perform both during manufacturing and in service. To obtain accurate information about these properties, mechanical testing is conducted, providing quantitative data that serves uh, as a basis for material selection and process design. And this table 2.1 have relative mechanical properties. They have strength, hardness, toughness, stiffness, and strain density. Okay, next slide is tension test, understanding stress-strain behavior. The tension test is the most widely used method to determine the mechanical properties of materials, including strength, ductility, toughness, elastic modulus, and strain hardening capability. This test requires a prepared specimen, which is usually solid and round, although flat or tubular shapes may also be used. The preparation of the specimen generally follows ISTM standard or other international specification. A typical specimen has an original gauge length of about 50 millimeter and a cross-sectional area with a diameter of approximately 12.5 millimeter. Once prepared, the specimen is mounted in a tension testing machine that is equipped with accessories and control, allowing the test to be conducted under different temperature and deformation rates. And this image, and the mid is fracture, and the top is curve of elastic stress and strain. Right. Next slide is stress strain curve. In a tension test, the specimen first show linear elastic behavior, elongation proportionally to the load and returning to its original shape when unloaded. Engineer stress is calculated as the applied load divided by the original cross-sectional area. Beyond the proportional limit, deformation becomes nonlinear and permanent. Deformation starts at the yield stress, often determined using the 0.2% offset method. As the specimen elongates, its cross-sectional area is decreased, and unloading above the yield stress follows a line parallel to the elastic slope, with continued loading. The stress reaches its maximum value, called the ultimate tensile strength or UTS, before decreasing. And this curve is stress theta P AO. This elastic is plastic and strain. And next, Ductility is the extent of plastic deformation a material undergoes before fracture. It is measured in two ways. The first is total elongation of the specimen, calculated as F mean LO 100, where if and LO are the final and original gauge lengths. The second is reduction of area, calculated as AO mean AF, where AO and AF are the original and final cross-sectional areas. Elongation and reduction of area are generally interrelated as shown for typical metals. The ductility of coke is zero, while ductile materials such as putty or chewing gum stretch and neck considerably before failure. In this table, they have stainless steel, copper and its alloy, aluminum alloys, and low carbon steel. Okay. Next, true stress and true strain. Engineer stress is based on the original cross-sectional area (AO) of the specimen, but as the specimen elongates, its instantaneous area becomes smaller. So engineering stress does not represent the actual stress. True stress is defined as the ratio of the load P to the actual instantaneous area A of the specimen. True strain is obtained obtained by considering incremental change in length and is calculated as ln L per LO. For small strain values, engineered and true strains are approximately equal, but they diverge as strain increases. Unlike engineered strains, true strains correspond to actual physical deformation. For example, if a 50 millimeter specimen is compressed to zero height, the engineered strain will be -1, but the true strain would be negative infinity, correctly describing infinite deformation. And this with load, stress, true stress, and true strain, extension strain, and this curve is down in behind. And then next slide is construction of stress strain curve. The engineered stress strain curve is obtained from the load elongation curve by dividing the load by the original cross-sectional area (AO) and the elongation by the original gauge length (LO), giving a curve with the same shape of the load as the load elongation curve. The stress-through strain curve are obtained by dividing the load by the instantaneous cross-sectional area and calculating true strain, with correction applied for three-dimensional stress in the naked region. The true strain curve can be expressed as theta k sigma n, where k is the strain coefficient and n is the strain hardening exponent. On a log plot, the slope equals n, representing strain hardening capacity. Data difference may arise from different specimen and source, with elastic region typical omitted so that the intercept represents the yield stress Y. The area under the true strain curve represents the energy per unit volume required for plastic deformation, and the total area up to fracture defines the thickness, indicating the energy absorbed before fracture. with toughness depending on both the height and width of the curve. Okay, next, strain at necking in a tension test. The onset of necking in a tension test specimen corresponds to the ultimate tensile strength of the material, where the slope of the load elongation curve is zero, and the cross-sectional area decreases faster than the material strain hardness. The true strain at the onset of necking is equal to the strain hardening exponent n. So a higher n allows greater strain before necking begins. Materials such as annealed copper, brass, and stainless steel have high n values and can be stretched more uniform than other metals. And this is a stick modulus, tensile strength, and yield strength and elongation is stable with the stress and temperature. Okay, next the compression test. The compression test is used to study material behavior under compressive stress, which is important in manufacturing processes such as forging, rolling, and extrusion. It is typically performed by compressing as a solid cylindrical specimen between two flat, lubricated disks. Though friction can cause bugging known as burling. To prevent buckling, the height-to-diameter ratio is kept below 3:1. Burling and friction make stress-strain curve harder to obtain, as friction increases to require compressive force. For ductile metal, true stress-strain curves from tension and compression concave, but brittle materials are generally strong and more ductile in compression. The Bouchinger effect occurs when a material loaded in tension and then in compression, so a lower yield stress in the opposite direction, also called strain softening, for brittle material like ceramic and glasses. A disc test is used where compression produces tensile stress that split the disc vertically. This method also has application in stainless tubing production. Next, torsion test. A workpiece can also experience shear strains, as in a punching, swagging, or metal cutting, and these properties are determined through a torsion test. This test is usually performed on a thin tubular specimen with a reduced cross-section to ensure uniform stress and strain distribution. Shear stress is calculated from torque, average radius, and thickness, while shear strain is determined from specimen length and angle of twist. The ratio of shear stress to shear strain in the elastic range is the shear modulus G, which is related to the modulus of elasticity. Additionally, the angle of twist to fracture, especially especially in torsion tests at elastic temperature, help estimate the forgivability of metal. The greater the twist before failure, the better the forgivability. Bending fracture test. Material respond to fracture loads. Preparing specimen from brittle materials, ceramic carbides, is difficult due to shaping machine surface defect, notch, and clamping alignment issues. Bend fracture test is commonly used for brittle materials. Specimen usually has a rectangular cross-section, load applied in two ways. One way is 3-point bending, load at one point, and the two is 4-point bending, look at 2 points. stresses tensile at the bottom surface, compressive at the top surface. Strength at the fracture in bending, modulus of fracture, transverse rupture strength. 4-point bending gives a lower modulus of rupture than 3-point bending because a large material volume is under the same bending moment, increase the chance of defect. Hardness test resistant to indentation and wear. Hardness is a commonly used property that reflects a material's strength, resistance to stretching, and resistance to wear, and it's generally defined as a resistant to permanent indentation. However, hardness is not considered a fundamental property because the measured value depends on the shape of the indentation and the applied load. In relation to strength, hardness often shows a positive correlation, as harder material typically possess higher strength. Although this relationship is not exact to the influence of testing conditions, to measure hardness, several testing procedures are applied such as Grinnell, Rockwell, and Vickers method, which use different types of indenters and loads. This procedure provide practical and comparative data that are especially useful in material selection and quality control. Hardness tests. Hardness tests. Various hardness tests have been developed using different indenters and loads. The brain tests measure hardness from indentation are using steel or tungsten carbide balls, while the Rockwell test measure penetration depth with different cell scales. The Vickers test use a diamond pyramid indenter and give consistent results across a wide hardness range, including nanoscale. The knob test is a micro-hardness method suitable for thin or brittle material and allow grains. Dynamic tests like the scleroscope and lab tests measure rebound with lab values convertible to Rockwell or Vickers. The most scale rank stretch resistant from Tag 1 to Diamond 10 for soft elastic material. The shear durometer test is used, and hot hardness test evaluate hardness at high temperature for tools and dies. This table shape of indentation Webriel retest in intersect view and hardness number. Hardness test. Hardness defined as resistant to permanent indentation can be considered similar to a compression test on a small surface volume. For cold-worked metals, hardness is about 3 times the yield stress, while for annealed metal it is about 5 times. Moreover, a relationship exists between the ultimate tensile strength (UTS) and the Brinell hardness habit for steels tested under a 3000 kilo load in SE units. Hardness testing procedure. For reliable hardness testing, the indenter must deform freely so it's distant from specimen edges, and specimen thickness are critical. The indenter should be placed at least 2 diameters away from edges, and thickness should be at least 10 times the penetration depth. Indentation must be spaced apart and large enough to represent bulk hardness. With light loads are used for small areas or allow constituents. Surface preparation is important, especially for rock wheel and micro hardness tests, often requiring polish hardness values from different tests can be converted, but caution is needed to material and indentation variables. Fatigue behavior under cycling loading. Definition: progressive structural damage due to repeated cycling stress, often below yield strength. Key measure correcting by S and curve stress as number of cycles to failure. Important responsible for over 90% of mechanical failures in surface application. Grab long-term deformation under load. Definition: time-dependent plastic deformation of material under constant load, especially at high temperatures. Takes primarily recurring, secondary, steady-state, and tertiary as accelerating to failure. Application: critical for turbines, boiler, and aerospace component operating under heat and stress. Impact testing: in many manufacturing operations and machinery, component materials are subject to impact or dynamic loading. A typical impact test uses a notched specimen broken by a swinging pendulum. In the Kirby test, the specimen is supported at both ends, while in the ISO test, it is supported at one end like a cantilever beam. The pendulum swing gives the energy dissipate, which is the impact toughness of the material. No quantitative relationship exists between Kirby and ISO test. Impact tests are useful for determining the ductile brittle transition temperature. Material with high impact resistance usually have high strength, high ductility, and high toughness, while notch sensitivity significant reduce impact toughness, especially in heat-treated metals, ceramic, and glasses. Failure and fracture. Failure is a critical aspect of material behavior since it affects material selection, manufacturing, methods, and surface life. It is generally classified into two types: fracture, ductile or brittle, and buckling. While usually undesirable, failure is sometimes intentional in design, such as inter-of types of container, shear pins for overload protection, perforated packaging, and screw caps for bottle. These they have cracked in different situations. This burning and this crack. Failure and fracture, ductile fracture. Ductile fracture occurs with plastic deformation before failure, starting with necking and void deformation that grow into cracks, often producing cup and cone fractures. Inclusion like oxides, carbides, or sulfide act as nucleation sites for void, with their effect depending on shape, hardness, distribution, and volume of friction. While voids may also form during casting of metalworking, the element of intrusion can cause mechanical firing, require proper working direction for strength and ductility. Many metals also exhibit a transition temperature where ductility and torque drop sharply due to factors such as composition, grain size, surface finish, and deformation rate. Additionally, strain aging in steel caused by carbon atoms binding this cohesion increased strain but reduced ductility, and when occurred at higher temperatures leads to blue grid lens. This with temperature ductility talks is on top. Transient temperatures in here. Brittle fracture. Brittle fracture occurs with little or no plastic deformation, usually along cleavage planes under maximum tensile stress, promoted by low temperature and high strain rate. It often shows granular surface in polycrystalline metal and can be transgranular or intergranular, depending on grain boundary condition, defect like crack, strands, or void accelerate crack propagation, leading to catastrophic failure, especially since brittle materials are much weaker in tension than compression. Fatigue fracture also occurs in a brittle manner, starting from small flaws and producing benchmark and striation. Fatigue strength can be improved by spinning, case hardening, fine surface finishing, and reducing impurities, but can be weakened by tensile stress, corrosion pits, or electroplating. Stress corrosion cracking causes ductile metal to fail in a brittle way under corrosive environments, often in brass or stainless steel, and it's mitigated by stress relief or annealing. Hydrogen embrittlement, especially severe in high-strain steels, reduce ductility and cause premature failure, with sources including melting, pickling, electroplating, welding, or atmospheric moisture. Residual stress. When workpiece undergo non-uniform plastic deformation, residual stress remains after forming and removal of external force, as in bending a metal bar. Initially, a linear elastic stress distribution occurs, then yielding in other fibers leads to permanent bending with a new stress distribution. Upon unloading, recovery is elastic, and the difference between stress distribution produces a residual stress pattern with compressive and tensile regions in static equilibrium. Removal or material or relaxation can disturb this equilibrium, cause warping. Residual stress may also result from temperature gradients during process, such as cooling off, casting off, forming producing non-uniform deformation. Residual stress, tensile residual stress on the surface are indesirable because they reduce fatigue lift and fracture strength, particularly in brittle or less ductile material, and may lead to stress cracking or stress corrosion cracking. Compressive, compressive residual stress are desirable and they can improve fatigue life and can be introduced by methods such as salt heating and surface rolling. Residual stress can be reduced or eliminated by stress relief annealing, further deformation such as stretching, or violation over time, which is colored by elevated temperature. This have before and after and distortion of part with residual stress after cutting or slitting. And a flat sheet or plate in this solid round rod and this thin wall tubing or pipe. Work head and temperature, energy interaction in material. Most mechanical work in plastic deformation converts into heat while 5 until 10% up to uh, 30% in some alloys is stored as elastic energy. The theoretical adiabatic temperature rise depends on deformation energy, density, and specific heat, with higher rise for material with large stress strain areas and low specific heat. Example is for a true strain of 1 are aluminium 75 Celsius, copper 140 Celsius, steel 280 Celsius, and titanium 570 Celsius. In practice, heat is partly lost to the environment, tools, and lubricants, so rapid process retain more heat, while slower ones show lower temperature increase. And this delta T is U per BC. Okay, that's all. Thank you.